All right, get ready to dive into some really fascinating machine learning research. We're looking at this paper towards understanding extrapolation, a causal lens. And it really gets into something that is kind of AI's Achilles heel, something we humans do naturally.
Yeah, it's true. Humans, we're fantastic at extrapolation, taking what we know and applying it to new situations, even when those situations are totally different from anything we've experienced before. But AI really struggles with this idea of making predictions on data outside of what it was trained on.
So extrapolation, that's the big challenge here. This paper is trying to help AI get a leg up, so to speak.
Exactly. And they're doing it by taking a causal approach. They're really trying to dig into the underlying mechanics of how data changes. And their argument is that if we can understand those causal relationships better, then we can actually build models that can do more than just recognize patterns. Models that can start to understand the world, or at least the piece of the world they're trained on.
Okay, I'm with you so far, but maybe an example would help.
Sure, let's think about image recognition. You've trained a model to recognize cats, but you've only shown it pictures of tabby cats. Now you show it a hairless Sphinx cat. A typical model might be totally thrown off because it looks so different.
Right, stuck on fur, stripes, those very specific tabby cat features.
Exactly. But a model with a causal lens would understand that being a cat is more than just those surface-level traits. It would recognize the underlying structure, the skeletal shape, maybe even the way it moves, the mischievous glint in its eye, that catness, even without the fur.
So it's about helping AI see past the superficial to understand the core essence of something. But how do these researchers actually propose to do that?
Well, they use this framework based on latent variables. These are variables that we can't directly observe, but they influence the data we see.
So like hidden puppet masters controlling things from behind the scenes.
That's a great analogy. And they break down this latent space into two parts. First, there's the invariant variable, which captures the essence of what we're trying to identify. In the cat example, this would be that inherent catness, regardless of breed, fur, or lighting.
Okay, that makes sense. So what about the second part of this latent space?
That's what they call the changing variable. This accounts for all those variations we see, like the background, the lighting, the angle the picture was taken from. You could think of it as the style or the context surrounding the invariant content.
So if we can pin down that invariant variable, then even if the style changes drastically, we can still recognize the core thing. We've cracked the code of extrapolation.
Exactly. But the challenge is figuring out how to identify that invariant variable. And the paper explores two scenarios that make this really tough: dense shifts and sparse shifts.
And shifts. Now that sounds a little intimidating.
They can be. Imagine you have a picture of a cat and the lighting changes dramatically. It impacts every single pixel in the image. That's a dense shift because the change permeates the whole data space.
So it's like trying to find a needle in a haystack blindfolded. How on earth do they propose to deal with that?
Well, they actually lay out some specific conditions, almost like mathematical rules, that determine when that invariant variable can still be reliably identified, even in the face of these dense shifts. And one crucial piece of this is that the invariant variable has to be what we call discrete. It can only take on a finite set of values. You can think of it as distinct categories.
Okay, so even though the style is changing a lot, we still have these anchors, these clear-cut categories.
Right, but there's another crucial part. The shift can't be too extreme. The target data, what we're trying to extrapolate to, needs to stay relatively close to what the model was trained on. Imagine it like a leash. You can give it some wiggle room, but if it goes too far out, you're lost.
Gotcha. So dense shifts, definitely a challenge, but manageable under the right conditions. Now, what about these sparse shifts? Do they offer a little more wiggle room?
In a way, they do. Let's go back to the cat picture, but this time only the background changes. The cat itself stays the same. That's a sparse shift. The change is localized. It's only affecting a specific part of the data.
So it should be easier to find the invariant variable then, right? We can focus on the cat itself, the core object of interest.
Exactly. And what's really interesting is that the paper argues that with sparse shifts, you can potentially extrapolate even when the changing variable changes drastically, as long as there's enough information left in the unchanged part of the data.
So even if we take that cat and put it on Mars, we can still recognize it as a cat.
Precisely. And that's where this idea of mechanistic dependence comes into play. The features tied to the invariant variable are all linked to each other in a meaningful way. They basically scream, "This is a cat," even when the background is totally alien.
This is all super insightful, but I'm guessing turning these theoretical ideas into algorithms is a whole other challenge.
Yeah. Absolutely. It's one thing to grasp the principles, it's another to actually build models that can use them. But that's what these researchers did, and the results are really impressive.
Okay, you've definitely piqued my interest. We've got this theory of dense and sparse shifts, this idea of a causal lens for AI. But how does it all actually work in practice?
Well, that's where things get really fun. Buckle up because we're about to enter the world of synthetic data, where researchers get to play God and create these data sets that perfectly embody these scenarios.
Sounds like my kind of AI sandbox. Can't wait to see what these models can do. So we're stepping into this world of synthetic data. I'm imagining these researchers in their virtual lab coats, creating these data sets to put this causal lens through its paces.
It's pretty ingenious, actually. By really carefully controlling how they create the data, they can simulate those dense and sparse shifts we were talking about, basically build this perfect testing ground for their theory.
So it's like they're running a controlled experiment. They get to isolate certain variables, tweak things, and see how the models respond. Can you give me an example? What does one of these synthetic data experiments actually look like?
Okay, so imagine a data set with all these data points. Each point is a combo of those latent variables, the invariant one and the changing one. You can think of it visually like a multidimensional space where the invariant variable, that determines the category, and then the changing variable controls where the point falls within that category.
Okay, so each point has a meaning based on its invariant variable, and then its location is based on the changing variable, like a map. Different regions are different categories, and the data points are scattered within those regions.
Yeah, that's a great way to picture it. Now, in the dense shift scenario, they allowed the changing variable values to move away from the origin, but they could only move within a certain radius. Remember, with dense shifts, the target data needs to stay kind of close to the source data.
Right, that leash concept.
Exactly, and they didn't stop there. They made the function that connects this latent space to the actual data we see. They made it super complex.
So they're really making things tough, a complex model, and intentionally shifting the data to try to trip it up.
Yeah, they set a pretty high bar. Then they tested their method against two other approaches. One, a model trained only on the source data, that's the naive approach, just ignoring the out-of-support problem altogether. And two, a method specifically for domain adaptation. That's a technique for dealing with shifts in data distribution.
Okay, so the first one's like the student who crammed but didn't really understand.
Yeah.
And the domain adaptation method is like this seasoned veteran.
Exactly. But keep in mind, even the veteran method isn't designed for this extreme extrapolation scenario. It's like trying to use a map of Boston to navigate Tokyo. Sure, some things might look similar, but the overall layout is totally different.
So how did their causal approach perform in this AI showdown?
The results were amazing, actually. Across all the different variations they tested, their method consistently did better than the other two. It was able to successfully identify that invariant variable, even when the data had shifted a lot, and that mapping function was super complex.
So even when they intentionally tried to make things difficult, their method still managed to find the essence of the data. Really impressive.
Yeah, it really highlights the unique challenges of extrapolation, where you're dealing with data that's completely outside of anything the model has seen before.
Okay, so in this very controlled environment, this causal lens really seems to work. But the real test is how it performs with real-world data, right? All that messy and unpredictable stuff.
You got it. Synthetic data is great for testing out theories, but the real world is a whole different beast. That's where things get really interesting.
All right, so we've seen this causal lens work beautifully in that nice, clean world of synthetic data. But now it's time for the ultimate test, real-world data. All that messy, unpredictable data that AI has to deal with in real life.
Exactly. It's time to see if this theory can really hold up when things get tough.
And I'm guessing they didn't go easy on it.
Not at all. They tackled image classification, specifically test time adaptation. This is where you're trying to get a model to adjust on the fly to a brand new data distribution. It's like giving your AI a crash course in how to adapt to a new environment.
Okay, so taking a model that's been trained on textbook examples and throwing it into the real world, where things are never that neat and tidy.
Precisely.
So what kind of real-world data sets did they use?
They chose some that are known for being particularly challenging, ImageNet-C and CFAR10C. These datasets take standard images and then they apply all sorts of corruptions like noise, blur, weather effects.
Really putting those models through the ringer?
Yeah, it's like they're trying to simulate all the unexpected things that AI might encounter out in the wild.
So a real trial by fire for this causal lens. And how do they actually implement it, using real data?
They put those two key strategies we talked about into action: generative adaptation and sparsity regularization. And they use a really cool method called MAETTT as their base.
MAETT, that sounds familiar.
It's one of those masked autoencoder approaches. It basically trains a model to reconstruct images where parts of the image are missing.
So it's learning to fill in the blanks.
Exactly. It forces the model to develop these really robust representations of the data, to understand what an image is, even with some information missing.
Like a detective solving a case with only partial evidence.
Exactly.
So how do they actually incorporate the causal lens into MAETTT?
They added in something called an entropy minimization loss during training.
Entropy, now that's a word that can be a little hard to grasp.
It basically measures uncertainty. So by minimizing entropy, they're encouraging the model to make really confident predictions that fit with what it learned from the original data.
So even when it encounters something new, it's trying to stick with what it knows. They're giving it a little nudge in the right direction. And what about sparsity regularization? How did that come into play?
Well, they tested that out with a state-of-the-art test time adaptation method called TESLA.
TESLA. Yet another one of those AI acronyms.
It stands for Test Time Self-Learning with Automatic Adversarial Augmentation. But the main thing to know is that it's really good at helping models adapt to new data.
And by adding sparsity constraints to TESLA,
Yeah.
they basically limited how much the model could change during this adaptation process. And that actually made it work better.
That's right. By constraining the changes, they essentially forced the model to hold on to what it learned from the source data.
So it's like saying, okay, you can adapt, but don't forget everything you already know.
Exactly.
It's amazing how these theoretical ideas like dense and sparse shifts, these causal relationships, how they can be turned into techniques that actually work in the real world. So what's the bottom line? Did this causal lens pass the real-world test?
The results were really impressive. Their modified MAETTT, it outperformed the original version. It was more accurate on those challenging, corrupted images. And adding sparsity constraints consistently boosted Tesla's performance across different datasets.
It sounds like this causal lens is more than just a theory.
Yeah.
It's a powerful tool for building AI systems that can handle the unexpected. Systems that are more robust and reliable, which is what we ultimately want.
Absolutely. But as with any new research, there are still a lot of open questions, things to explore further.
Of course, always more to learn.
For example, the specific conditions they identified for successful extrapolation, they might be too strict in some cases. And figuring out exactly how to balance different aspects of the training process, that's still a work in progress.
But it's definitely a big step forward. It's moving us closer to AI systems that can truly think on their feet. Systems that can navigate unfamiliar territory without falling apart. And that brings us to our final thought for all of you listening out there. If AI has such a hard time with this idea of extrapolation, taking what it knows and applying it to new situations, how do we humans do it so easily? Are our brains wired differently? Or are there some deeper connections between the way we think and the principles they've uncovered in this paper? Something to ponder as you go about your day. Until next time.